Hello, lovely people. It has been over a decade since I last stood here, terrified, in front of such an august and amazing audience. It's lovely to be back in town, lovely to be back here at the Great International Developer Summit. So I'm Jim. I work at Neo4j, the graph database company. Not going to talk too much about graph databases this morning. Plenty of talks about graph databases throughout the conference. I'll be talking about graph databases and Gen AI tomorrow. Today, I want to talk about distributed systems. Who loves distributed systems? Woohoo! Who hates distributed systems? Woohoo! You're both right. Yeah? Distributed systems are wonderful and terrible, and I'm going to teach you everything I know about distributed systems in 15 minutes. But first, let me tell you a personal story. So I am a working class Englishman. I am the first person in my family to get any school qualifications in the whole of my ancestry. And I'm the first person in my family to go to university and get an undergraduate degree. I'm the first and currently only person in my whole family to have a PhD. Now, you may be wondering what... That was genuinely surprising. Thank you. That's not the point I'm going to make. The point is that my mum is terribly proud of... No, I misspoke. My mum was terribly proud of me. Because our Jimmy, she always uses the diminutive on me, our Jimmy. I don't get Dr. Weber from her, our Jimmy, always. Our Jimmy has got a PhD, and she's very proud. She can brag to the neighbors. So she asked me, our Jimmy, what is it that you do? I said, well, Mum, I work on something called consensus. And she says, what's that? Well, I'm like, it's quite complicated, but basically, and you can see the expectation in her face, that I'm going to say something profound. Like if one computer say, thinks of a number, let's say 10, expectation. And then another computer, I make sure it also thinks of the number 10 and stores that. Oh, that was damning. She said, the way she said, oh, that was hurtful, right? And I get it, right? Because it sounds so easy. You've got a few computers and they all just have to store the same thing, right? And it seems so easy. But it's not easy, right? Because things go wrong. And when things go wrong, it doesn't prevent other things from going wrong. And while you're putting right the things that have gone wrong, other things can still go wrong, right? That's what makes consensus such an interesting problem. The world is full of entropy. The world is a garbage fire, and we have to, in small quanta, make good progress while the wind's in our favor. So I'm going to teach you about something called Raft. Raft is a wonderful, humane protocol. Raft actually comes from this idea of keeping logs tied together. So, of course, underneath most databases, there is a log, which you can think of as a fancy linked list. And if you can tie those logs together, you can keep them in sync so that two or more databases can stay synchronized. And the wonderful thing about Raft, the people that built it was John Oosterhout, the guy that wrote Tickle. If you're sufficiently old, I'm looking for the greybeards to nod along to this. Not as much nodding, one greybeard nodding along, and you've had a shave. So it's not even bearded greybeard. John Oosterhout is wonderful. He's a polyglot, mathematician, computer scientist, awesome person. And he has this idea along with Diego Ongaro, the distributed consensus protocols, things like Paxos. Who's heard of Paxos? Who understands Paxos? You're lying. Nobody understands Paxos, even the people that created it. It's too hard. We used to have Paxos in Neo4j. At the time, we had about 20 engineers who had worked on it. I had about 21 opinions on how it worked, right? Raft doesn't do that. Raft just says, simplify everything, because in distributed systems, complexity is where the bugs lie. And in distributed systems, bugs are subtle and complex and catastrophic. So it's better to have a less optimized system that's simple than an optimized system that's hard, because the optimized system is simply more risky. So I'm sorry to the very brainy people that built and understand Paxos, but you did it wrong. Raft, on the other hand, is very easy. Has this idea that we keep logs together. So here's an animation of Raft. And what's going on is that one of the servers in this cluster gets elected as the leader. And its job is to suggest to the followers, hey, would you like to append this value at this index in your log? Having reached the basis that we've previously appended the same thing at similar indexes. And so that's all it does. It's effectively saying, can you append this? Yes, I can. And if enough of a majority of the servers say, yes, I can append, then the leader can say, okay, enough people agree, let's commit. And this applies not only to the data that you'd like to store, but it also applies to the topology of the cluster. So you've got everything you need written down in a majority of the logs. So it's a safe, fault-tolerant system, and it means that even if the leader fails, as it does in this animation, someone else that has an equivalent log can pick up and continue processing. So it's a non-blocking consensus protocol that ties these logs together. And it's lovely. Honestly, you could read the short paper in that this evening and it will delight you. And it has some really nice properties. So it keeps logs tied together, keeps cluster membership and data together. Everything's simple. Raft decisions are always made by a simple majority. Now, the clever computer scientists will tell you, you don't need majorities for quorums. You can do things like trees and rows and all sorts of clever stuff to mean that a minority of deciders can make a decision. But by God, when there's a failure, unpicking that mess is horrible. And Raft just says, no, do the simple thing. If a majority wants X, X it is. Simple to recover from. So anyone can call an election, and ultimately elections are decided by who has the most up-to-date log in the current era, in the current clock tick. And if two or more servers are equally valid as the leader, you'll toss a coin to determine who it is. And so this goes on. Note that in the logs that you saw earlier, there is both appended and committed. And entries, data that's being appended, is at risk. It may be truncated, but data is committed into the logs, is committed in a majority, and it will never change. It's immutable forever. So it's a really nice thing to recover from, because remember, distributed systems are a garbage file. Yeah. You didn't get taught that at university, did you? The guy with the arm patches and the tweed didn't tell you that distributed systems are a garbage file, but they are. So how does it work? You effectively, as I said, you move from appended to committed to applied. But can you reason about consistency? Here's an app that you've just built. And as a user, it says I need to log in to continue my purchase. So I log in, or I need to create a username and password. So I can do that. So I'll create my username and password in order to continue my purchase. No account found. Wait, what just happened there? That's an awful workflow for a user. What happened there? I'll tell you what happened there. Eventual consistency. I created an account. It got stuck on one replica. It hasn't yet replicated to the next replica. When I go to log in, I happen to hit that replica and things go to crap. This is terrible. You just lost a customer. So what do you good folks do? Thread.sleep 1000, right? You evil bastards. Never do that, right? That's terrible. So, and the thing that you need to know about this, in all distributed systems, because of this thing called FLP by Fisher, Lynch, and Patterson, hence FLP. Who knows CAP theorem? Who's ever heard of that? Lots of arguments about that about a decade ago. This is older and better magic than CAP theorem. This basically tells you that distributed systems do not work. But there is a window of time where computers just manage to hold their shit together for long enough, then you can get some useful work out of them. But in general, distributed systems don't work, and that's proven in this paper. There's always a trade-off between availability and reliability. To make things available, you have to trade off reliability. To make things reliable, you have to trade off availability. That's an underpinning fact that underpins our entire discipline. So then, given that, can you read what you write? Can you avoid situations where you create an account only to be told you don't have an account? And in fact, even in something like Raft, which is a strongly consistent consensus protocol, things are always ahead or behind each other, because that's the way asynchronous works, right? That's the way computers work. That's the way networks work. You will never have a perfectly synchronized system. It's not the way the universe works, sadly. So even in Raft, some logs will be ahead or behind each other, and that's normal behavior. So let's see what happens with Raft again. So I need to log in to continue my purchase. Oh, actually, I need to make a new username password, account not found. That sucks. But what's even worse is if I did try it a few minutes later, that says login successful if you have a projector that has high enough resolution, by the way. That's not some cunning thing. And it does work. And in fact, in a way, that's even worse, right? That it didn't work, but then I waited for a second and then it did work. Like things should either work or not work, right? This is like a Byzantine fault. This is computers messing with me in the worst possible way, right? Absolutely hate that. Why didn't this work? Why did it work this time? Because of time. Time passed. So what's happening was, down at the Raft level, we did create a count. Some replication was happening. As you can see, I replicated into a majority here, records 10 and 11, and the account was created. But then when I came to log in, what happens is I hit this replica here. You can see that record 10 and 11, my username and password, haven't reached this machine yet, but they will, and they must, because the majority of the cluster has committed them, but they haven't hit here yet. If I wait a moment, then I will get it. So what I can do is I can wrap this in a causal boundary, effectively turn my database into something that looks like a variable in your programming language, right? It'd be really weird if you said int I equals 10, and then you said int I, and it said 11, right? Now, computers, trust me, they do work like that under the covers, right? Computers are themselves asynchronous networks under the covers, and the only reason computers seem to work is that we have these magical things called memory barriers. In distributed systems, we don't have memory barriers, but we have other things that can help. One of the things is a causal barrier. In Neo4j, we use the term bookmark because at Neo4j, we're bad at naming things. For example, we're called Neo4j, which is a terrible name. It's a really good Git hash. It's a really terrible name for a product. So we've got these things called bookmarks, and bookmarks tell you the transaction ID of the last transaction that you observed. So you can do this again with causal consistency. So you create a user, it gets committed in a majority, so now we're committed, but we send back the transaction ID where that record was committed. Now, when I come to the read channel, I provide the bookmark as a parameter, and what will happen is I'll be slightly delayed at the replica that receives that request until the record has replicated, as Raft will soon enough do within the next few milliseconds. Then I can safely run the query and the login is successful. So you've got the interesting interplay of two different approaches here. You've got a strongly consistent consensus protocol, which is Raft, and a causal layer on the top that means you never go back in time, right? So one of the big Achilles heels of distributed systems is that you go back in time so often. If you're going to write this, it's trivial. You grab a bookmark from the transaction ID, and on the read side, you provide the bookmark as a parameter to your begin transaction. So it's trivial to use. You opt in, but it's super easy to use, and you'll never go back in time. So takeaways. Raft, as a non-blocking distributed consensus system, is amazing. It's safe, it's highly performant once you've optimized it, and there are very few places for bugs to hide. You know, given what you've learned in this 15 minutes, you're in a very good place to be able to go and explore Raft further yourselves. If you wrap Raft in a causal barrier, you get the best of both worlds. You enable Raft to run over a wide area network, but you preserve correctness from the user's point of view. I think that's very important, right? Users don't like it when they have to refresh their app or press, F5 on their website. It gives a really poor user experience. We shouldn't let the details of murky distributed systems thing leak through to the user interface. And you certainly shouldn't be putting thread.sleep1000 into your code as if that magically fixes distributed systems problems, despite the fact it does appear to magically fix most distributed systems problems. Distributed systems are still hard. They shouldn't be the first thing that you reach for when you're developing a business information system, but they're going to be necessary for some parts of your solution. Look at the things that the Red Hat guys talked about earlier, right? An interesting interplay of a bunch of distributed systems. But we do now have the underlay to be able to make these systems reliable so that we can present them to end users. If any of this has piqued your interest, I would recommend Unmesh Josh's book. It's an excellent starter, very friendly, written in the kind of pattern language. I think the ThoughtWorks folks are here somewhere. Unmesh works for them, so go hit up the ThoughtWorks folks. If you want to come talk to me about graphs, distributed systems, and all sorts of fun, I'll be on the Neo4j stand all day today, and I'll be speaking about graphs and LLMs tomorrow. So thank you very much for paying attention for these 14 minutes. I hope you have a spectacular day. Thank you all.